Hello, my name is Omar Darwish, and I'll be presenting over Rowhammer, which is a class of physical fault manipulation in memory that came about in 2015 from a research paper titled "Flipping Bits in Memory Without Accessing Them," which was written by a collaboration of these researchers from Carnegie Mellon University and Intel Labs. So we'll be going over what memory actually is, how it fails, what these researchers were able to do with these failures, how additional researchers took these failures and crafted them into security impacts, and what we can detect from them, and if we could detect this class of problems. So Rowhammer works by abusing some physical characteristics of modern memory, and it depends on these characteristics interacting in certain ways and causing certain failures. The most basic component of memory, specifically the one that's susceptible to Rowhammer, is the DRAM cell. And it's basically a transistor, a capacitor, and some wires that specify the word line and the bit line. These are two wires that make up the address of a cell. So this top part is the access transistor, and this bottom part is the storage capacitor. And what we want to do from the cell, what we want to be able to do with the cell is to be able to produce a charge, have it stored in the capacitor, and then read that charge later. So whenever we want to read a charge, we send a high voltage on the word line, which activates the access transistor, and then we read the voltage on the bit line. And if the bit line voltage is high after the transistor is activated, then we know that the capacitor was storing a charge, and that was a logical 1. And if there is no voltage on the bit line, or it's low, then that voltage was not being stored on, then that charge was not being stored on the capacitor, and that's a logical 0. And every time we do a read, we consume the charge that was stored, so reading is a destructive behavior. And we'll see how we can get around that later. Similarly, to write to a memory cell, we again activate the word line. And then if we want to write a 1 into the capacitor, then we produce a charge on the bit line, which will then be stored on one of the capacitor plates. And then the next time we want to read it, then this stored capacitor charge will come back out through the bit line, and we will be able to read the logical 1 that we wrote. If we want to write a logical 0, so we activate the word line and do not produce any current on the bit line. This means that the charge that may have existed before in this cell will drain out, but we don't care because we're not reading the bit line. And the next time we go and read the cell, it will not produce a charge, and it will be read as a logical 0. So 1 or 2 memory cells is not very useful. Real applications need hundreds, and real applications need billions of these cells. So we need a systematic way to organize them. So we organize cells by a grid of word lines and bit lines. And whenever we activate a word line, it will activate all of the access transistors for every cell in that word line. But this isn't precise enough. So we can attain more precision by adding a couple of different components. We do this by adding a decoder, a buffer, some amplifiers, and a multiplexer. And every group of cells that shares these components is called a bank. And there are many banks per chips, and there are many chips per memory modules. And the memory modules are the things that you, if you had experience building computers, or you've looked at like PCB diagrams of in electronics with memory, you'll see that it's like a rectangular block with many square blocks on them. The rectangular block is the memory module, the square blocks are the chips, and inside of them are these banks that share these components. So the decoder, what it does is it takes an incoming word address, figures out which one of the word lines it needs to activate, and it raises that specific word line high. And what that does is that it activates all the access transistors for all those cells within that word line. And once the access transistors are active for a cell, then charges begin to flow, and then they reach the next component, which is a sense amplifier. And a sense amplifier, what it does is it consumes these signals, And for some given threshold, if the incoming signal from the cell is greater than that threshold, then it gets passed off to the word buffer as a logical 1. And if it's lower than a threshold, then no signal is propagated to the buffer. And this is important because each cell has components that are susceptible to noise, and they may not produce specific exact values every time. So we operate on them using a threshold. And this is important down the line because there is a range of acceptable values for what is deemed a logical 1 and a range of acceptable values for what is deemed to be a logical 0. And then once they pass through the amplifiers, they get stored in a word buffer, which basically will hold all the values for all the cells that were activated during that word line. And again, because reading charges from these cells is destructive, this buffer is super important in being able to write back the values to the cells that stored the original charge. And this process of writing back these charges is called a refresh, and it's what gives dynamic RAM its name, as opposed to static RAM, which does not need to be refreshed because read operations on that type of RAM are not destructive. So after the word buffer, they get passed to a component called a multiplexer, which again takes part of the address, and it understands which of the cells the memory controller was intending to read or write to. So it takes all of the incoming signals and only picks out the ones it's interested in. So whenever we want to write to a row, it takes 3 steps. The first row, whenever we want to write to a row in a bank, it takes, we first have to open it. And opening a row is basically raising that row's word line, which starts transferring all the cells' incoming charges to the buffers. We then read those charges from the buffer and then refresh the cells. And then after we're done with that row, we must first bring the word line back down, which shuts off their access transistors, and the row buffer is then cleared. So this is a costly operation, and we try to optimize this, or the memory controller in a CPU architecture tries to reduce the number of times that these operations happen. So the model that we just described assumes that manufacturing was perfect, that there's no excessive noise for each component, and that the components don't interfere with each other, but that is not the case in the real world. And we'll take a look at simple failures in memory. The first one is a manufacturing defect. It happens whenever 2 conducting components accidentally touch. This creates a short circuit, and it may alter the design of the circuit, which is unintentional. I believe this is the easiest one to detect for the manufacturer, and it has pretty noticeable defects. The second one is electromagnetic coupling, where one source through its operation may accidentally interact with another source unintentionally, and it does this through a couple of different means. If there is a inductive component in one part and an inductive component in another, then a current may be induced in the victim component by current being run through the source component. It's almost like the coil. It is like the coil experiments you may have done in high school physics, where you run current through some kind of magnet, and then you see the other magnet also having a current. Conductive interference happens whenever 2 components are accidentally linked. This may happen in bridging components, where if you apply charge to one source, it also applies charge to the victim source. If 2 components have capacitive components, then charge accumulating on one end may cause charge to accumulate on the other, and again, induce a current in the victim. And then finally, there's radiative coupling, where one source may be putting out a signal and another source may be receiving that signal unintentionally. So these coupling phenomena happen more often whenever components are smaller, because they're more susceptible to noise, and when components are packed more closely together, as is the case for modern manufacturing, because of a demand in higher capacity, which requires smaller components packed more closely together. And the third uh, memory fault that we're going to look at is hot carrier injection. This one needs a little bit more of a electronics background, but basically, sometimes a transistor can fail where it's permanently toggled on if in the past it's being switched on and off very frequently for an extended period. And there's a fantastic video that goes over why this property may be useful in some applications and why it's detrimental in most cases. This is actually one of the reasons why flash memory has a limited number of reads and writes. It's because of this specific property. So as I said earlier, faults are more likely to happen as components get smaller and as more components are packed into a smaller area. In the recent years, memory sizes have been doubling in relatively short amounts of time, which produces demand to create smaller components packed more closely. And from the manufacturer's perspective, they used to consider the faults like this reliability issues and not necessarily security issues. But Rowhammer takes these issues and it transfers them from a reliability issue into a security issue. And the idea is really simple. For a victim row in some bank of memory, what you want to do is you want to keep reading from its neighbors over and over again very quickly, and then hope that by passing current through adjacent neighbors that one of these cells in your target row experiences interference and its value is changed. So you hammer its neighbors aggressively and then poll to see if any value within the row has changed. And this happens because some memory faults in manufacturing may not have been caught. There might be some disturbances that happen when nearby components are operating. And if these disturbances produce more charge on a nearby cell, then the resulting charge may be higher than some threshold that determines if it's a 1, or if it reduces charge, then the resulting charge may fall below the threshold that makes it a logical 0. And whenever these changes occur, the refresh mechanism will then propagate them back and consider them to be the new value of that cell. Because bit flips are based on physical, unchanging characteristics of the memory cell itself, once you discover that a cell is prone to flipping, it's very likely that you can make it flip in the future again. So exploits of this nature tend to be pretty reliable, which is very detrimental to the security of a system. And the researchers provide some sample code to go about triggering this. They give the left side code, which reads from 2 addresses, clears the cache for both, clears out the memory buffer array, and then again loops back and does it again. And the right side reads from 1 address, clears the value of that cache, clears out the memory buffer array, and again goes back to the loop. The right code does not work because we're reading the same row over and over again, and the memory controller is trying to reduce the number of times it opens and closes rows. So it will optimize whenever it encounters this set of instructions. It'll open the row 1 time, keep reading from it as the loop keeps going, and when this block is passed, but it's not possible for this block to pass at the moment, the memory controller row again will close out that row. So this keeps the word line high, but it does not cause any bit flips, and the researchers believe that disturbances in DRAM memory only happen if you're toggling the word line high and low very frequently, which this code does not do. This code, however, does. What it does is it reads from X and Y, which are chosen to be 2 addresses from memory rows that happen to be in the same bank. And because you cannot read multiple rows within a bank simultaneously, one row must be open and closed before the next one is opened and read. So this forces the memory controller to have to raise the word line for each address row over and over again, which has a higher chance of inducing a bit flip in the neighbors of X and Y, in the neighboring rows of X and Y. This is what's called row hammering. Because you're opening the row over and over again, you're hammering it with the intention of trying to induce a bit flip somewhere. For a higher chance of causing a bit flip in your target, what you want to do is you want to choose X and Y such that they are neighbors either above and below your target row. This is called double-sided row hammering, which aids in producing more bit flips, as we'll see in how Google uses this to produce an exploit. As you may have noticed that we have a couple of different caching and cache flushing instructions, and this is important because memory access is relatively expensive as compared to CPU caches like L1 through L4. And for this exploit to work, we need to interact with the memory controller itself as frequently as possible by bypassing the browser cache. And we do that by saying, hey, if you cache the value for these addresses, get rid of it. Don't worry about it. We don't want it. Talk to the memory directly. Also, if the memory controller has any, if the memory controller's buffer has any values, it should be flushed out directly because sometimes memory reads are buffered before they're actually consumed from, memory reads and writes are buffered before they're actually consumed from the main memory. And again, this is a performance enhancement. So we want to bypass both of these mechanisms and talk to the main memory directly. So the researchers also suggested a couple of mitigation techniques to reduce the chance of row hammering being successful. The first one is kind of obvious. They suggested that manufacturers should make better chips. Obviously, if the manufacturer could improve their circuit design, they could figure out how to reduce bridging faults, manufacturing bridging faults or coupling interactions, or they could figure out if there are dead cells at the factory and retire them. But this is not a permanent solution because as demand for greater memory with higher performance continues, we will likely run into the same issue as components get smaller. Another suggestion is using error correcting memory. And what this does is it is a bank of memory cells that will correct detected errors in other memory cells before they get read or written to. But this is expensive and it's usually used in servers. And it also reduces the overall capacity of the memory module. So this is not a universal solution. This is for an immediate fix to critical applications for servers. The other mitigations are more software-based, and they suggest the brute force solution is to refresh all memory more frequently. The current DRAM, the current DDR3 and 4 recommendations are to refresh each memory cell once every 64 milliseconds. But if we decrease that refresh period, we are more likely to flush out bit flips. But this comes at a huge performance penalty, obviously, because the more time spent by the memory controller flushing rows, the less time it spends doing reads and writes. And then Google suggests making the CL flush instruction in the x86-64 architecture a privileged instruction. They argue that not many legitimate userland processes have a need to clear out the memory cache directly, and it's usually some behavior, and it's usually behavior that a kernel driver or device driver needs to do, and that's usually not something that a userland process needs to do. Another suggestion from the paper authors is to try and identify rows that are being accessed constantly, and they're calling these hot rows, but this is not simple. It would greatly increase the complexity of the chip design because counters for each row would be very expensive. So one naive assumption is that if you could use Bloom filters or other similar bucketing and hashing algorithms, maybe you could reduce the number of counters. But because these algorithms rely on hash functions, they will inevitably result in some collisions. And hash collisions in this application are very expensive because if one row needs to be refreshed and it collides, and its hash collides with other rows, and those other rows will be needlessly refreshed, which is expensive. So the researchers' final solution is to try and refresh adjacent rows with some probability. And they reason that every time you access a row, you refresh its neighbors with some low probability. And if a row is being hammered, then its neighbors have a higher chance of being refreshed, which gets rid of these bit flips. So this is all theory for now, but some researchers at Google's Project Zero took this information and crafted it into a working exploit. And they did this by first trying to find out for their target rows who the neighbor rows are, um, and then how do they increase the likelihood of bit flips happening in that row. And then once you determine which rows and what methods cause bit flips in which rows, how do you use that in a meaningful exploit where only a single bit or a handful of bits is all that's really necessary? And they propose um, a couple of different things. So for finding neighbors, uh, they need to find two addresses within the same row in the same bank. And the brute force solution is to have a working knowledge of how a CPU's memory controller maps physical addresses to virtual. So the brute force solution is to figure out how the CPU maps physical addresses and how they fall within a DRAM's row, column, and bank layout, which is not trivial at all, and it's very expensive and costly to determine. Another suggestion that they used is picking addresses randomly. If we assume that a memory module has 16 banks, then we have a 1 in 16 chance of grabbing two addresses within the same bank, or actually 1 in 32 chance of grabbing two addresses in the same bank. And then finally, they can use timing. If they pick two addresses, and they realize that reading them sequentially is slower than picking two other chances, then it's very likely that these two addresses fall within the same bank. Because you cannot read multiple rows from the same bank without closing the first, it'll increase the amount of time necessary to read these two rows. So timing is a channel that that leaks some information about these rows. And then they increase success if they first trying to figure out like how much memory is within each row for each architecture, and this is called the row offset. So if you understand how many cells are in each row, then you can be more precise with understanding where each row ends and the next one starts. And once you know that, it's easier to do double-sided row hammering, which is grabbing both upper and lower neighbors of a target row. And then finally, a simple one is just to read the rows read the rows more often per loop. Again, more access causes a higher chance of bit flips. So they took these strategies and they managed to produce two working exploits. One is for Google's native client, and the other one was a kernel privilege escalation in Linux. So native client is Google's sandboxing system that lets you run untrusted applications that are written for x86, 64, and other architectures. And as it's running, it uses a validator to check that the program's code is safe, and it uses a subset of the instruction set, which they believe is safe. Like most other security mechanisms, it makes the assumption that if memory is written to, it does not change unless it's written to again. One part of the sandboxing logic is to try and limit where the program code can jump. So it does this by trying to figure out what the intended target is, doing some bit math, and then adding this intended target after the start of the sandbox, and then jumping to it. But this could fail if you could manipulate where the jump instruction is going to. So if a bit flip occurs for the register number that jump is taking, instead of jumping to the value of whatever register RAX is carrying, it may be jumping to a value of a different register. So for example, if a flip happens in the lower order bits of the register number, then this could be transformed from jump to the value of whatever's in RAX to jump to the value of whatever's in RCX. And this is significant because RCX is an unconstrained register, which means that you can jump arbitrarily across the memory space if this happens. And if you're able to jump to arbitrary spaces, then that means you can bypass instruction alignment. And if you can bypass instruction alignment, then you can start smuggling excuse me, unintended instructions, almost like return-oriented programming gadgets. You can tell the CPU that to jump in the middle of some memory space, which could be reinterpreted as a different instruction than what was actually written in the program. and this is significant. And then the other exploit they provided is a kernel privilege escalation. So this one's a little bit over my head, so I might have this incorrect, but from my understanding, they have a userland process which allocates a large chunk of memory, and then it sprays this memory region with a bunch of fake page table entries, which basically, for a process in an operating system with virtual memory, describes which virtual pages are allocated to that process by the kernel usually. So within these fake pages, they include a special marker value, and then they try and Rowhammer the page table entry for the attacking process's physical page. And they want to flip the lower order bits of this page table entry, because if they flip a higher order bit, it most likely will start pointing to a address space that falls outside of the physical memory. But if you flip a lower order bit, then it'll most likely point to some other region in memory, which, because they allocated so many fake page tables across a large chunk of memory, likely falls within a attacker managed memory region. So once this attack is carried out, they can't directly ask the kernel if, that's incorrect. Once this attack is carried out and they notice that one of their fake page tables no longer has this access marker, then it is safe to assume that they have been granted, that the attacking process has been granted access to a region of memory that it didn't have before. And if that is the case, then that means that the page table entry is relying on one of the fake page tables that were that are writable by the attacking process, and this means that they have the attacking process has arbitrary read and write access across the memory space of the target host, which is again devastating. So is there any way to detect these class of acts? Is there any way to detect these class of attacks? That is an ongoing field of research, actually, because memory reads are not 100% malicious. They're required and necessary for normal operation. Memory reads to the same location are not malicious because, again, you could be in a loop, constantly reading and updating a counter. So the interim solution at the moment to try and detect this is to see how many times we're hitting the cache and how many times we're having misses. So a typical healthy system should not have an excessive number of cache misses. This is, even for a heavily underload system, it usually will be able to hit the cache sufficiently well. So if we notice that our system is constantly missing the cache, then this could be a sign that someone is trying to do a Rowhammer attack. And Linux and other operating systems surfaces this information from hardware performance counters. But then the other question is, like, what do you do if you do detect an attack? It's kind of unclear. How do you confirm that this is an attack? Currently, it's still a field of research that is sure to see more development in the future. So finally, what this class of attacks has taught us is that the pursuit of performance has unintentional side effects. And again, we see this in the CPU side with branch prediction, security bugs like the case of Spectre and Meltdown. And then sometimes what the manufacturer deems as a reliability issue is more serious than what was initially thought after some researchers have time to go in and actually evaluate these issues. And because these issues are hardware-based, it's very hard to mitigate. For Rowhammer specifically, real-world exploits are still being found, which only require a small number of bit flips. We're constantly seeing where a small number of flips could have a profound effect on the system. And as we've noticed, detection is difficult for these classes of problems, and it's still an ongoing field of research. We're going to see more development in this area. There was actually recently a talk from Baidu on how to attack current mitigations for this technique. So this field of this class of exploits is still young, and I greatly encourage you to keep following along and check out the rest of these sources for this information. Thank you for your time.